So, everyone, thank you for waiting. It's a long wait for today's talk to begin, which means it's gonna be awesome and excellent. So I'm gonna do a very short introduction to Dr. Wookyoung Lee before she starts her talk today. I personally knew Wookyoung back in I don't know when, so maybe at least 5 years ago. When
No,
I
it's about the
was
10 years ago.
10 years ago? Okay, if it's 10
I
years
think
ago,
so.
I was still a student. Yeah, I was still a student in the States. At the time, Wookyoung was doing her postdoc or researcher, visiting scholar at John Hopkins University. And we just start knowing each other and also some folks at the CETA community. Uh, for several students here, you might have no CEDAR workshop already, or maybe will learn about it in the future. And Wookyoung got her degrees mainly in Korea, but as I mentioned earlier, she went to John Hopkins to do more studies and then become a senior and now principal researchers at CASI. And CASI is Korean Astronomy and Space Science Institute. Her talk today titled Exploring the Ionosphere and Aurora, Cassie's current project and future missions. So with further ado, let's welcome Wookyoung Lee. Dr. Wookyoung Lee, thank you. It's only me applauding.
No, hi, greetings everyone. So I need to share my screen, right? So let's start. Already 20 minutes are gone, so sorry for the late. And yeah, I'm getting older than older, and it is not familiar with those kind of this system. So sorry about that. Yep. As the CC introduced me, then my name is Wookyoung, and I'm working at Korea Astronomy and Space Science Institute. We call it CASI. As part of my presentation, I will be introducing ongoing projects which I'm currently leading to monitor the ionosphere. So my presentation consists of 4 parts. The first, I will provide a brief overview of CASI and GNSS research group. Following that, I will discuss our ionospheric monitoring projects, which involved both ground-based GNSS and the space-based rockets. And lastly, I will share details about the new space mission Athena for international collaboration. CASI is the National Research Institute for Astronomy and Space Science in Korea. This year is 5th anniversary of our institute. Our research field spans across various domains, including astronomy and planetary science and heliophysics and space situational awareness. Over the years, we have been dedicated ourselves to development of space programs for astronomy and space science. Allow me to introduce our GNSS research group at CASI. GNSS stands for Global Navigation Satellite System and enables us to receive signals from GNSS satellite to determine their position and timing. The most well-known GNSS is GPS, developed by the United States. And additionally, there's Galileo, European system, and GLONASS, the Russian system, and Beidou, the Chinese system. Within GNSS, the International GNSS Service serves as an international organization for GNSS data and products. Globally, there are over 500 IGS stations with 8 stations located in Korea. Interestingly, the very first IGS station in Korea is houses within our institute, CASI. IGS Global Data Center they play a crucial role in archiving the data from IGS stations and distributing it to the user community. Now there are 6 IGS global data centers worldwide, with CASI operating the first IGS global data center in Asia since 2006. So in addition to our global data center, we manage a regional GNSS network consisting of 9 stations in Korea and 2 stations abroad. We provide access to GNSS data from our network through FTP service. Our research primarily focus on the natural hazard monitoring using GNSS data, which includes seismic monitoring and tropospheric monitoring, the tropospheric PWB for numerical weather prediction, and notably ionospheric TEC, total electron contents. Furthermore, we have deployed a GPS radio occultation receiver on Korean satellite CAMSAT-5. So this collaboration has fostered a long-term partnership with UCAR Cosmic for data processing and distribution. Now, I will introduce our CASI near real-time ionospheric monitoring system. This is kind of an ongoing project. So I don't know how familiar everyone is with this term ionosphere. I believe that some students for the CC, students of the CC are very familiar with the ionosphere, upper atmosphere, but not many students or not many people, they are not familiar with the ionosphere. So I will introduce the ionosphere at first. The ionosphere that constitutes the ionized portion of our atmosphere, so extending up to 1,000 kilometers is a huge and vast region. The key parameter that defining the ionosphere is electron or the plasma density, and this plasma density fluctuated significantly with the local time, season, and solar cycle. Sorry for the Korean in the figure. The variations in plasma density significantly impact radio propagation. So especially the sudden changes can disrupt radio communication and navigation system like a GPS. So the monitoring the ionosphere is essential to maintain the performance of the systems. Indeed, the ionosphere represents the largest error source in GPS positioning, causing the signal delays and the scintillations. However, we can use this delay in GNSS signal to drive ionospheric plasma density. So this drive parameter is known as the total electron contents, TEC, and representing the column density of electron between the receiver and GPS satellite. So IGS operation centers drive the TC from data collected by 200 to 300 GNSS stations and producing the global ionospheric maps. These maps are very instrumental in monitoring large-scale ionospheric variations, but GIM offer only low spatial resolution. So we need a regional ionospheric map with a denser network. Okay. So this animation demonstrates the propagation of ionospheric perturbations triggered by a Tohoku earthquake in 2011. Use TC acquired from the extensive and densely distributed GNSS network, we can capture the details of smaller scale disturbances and irregularities within the ionosphere. So that's why we started this near real-time monitoring system project. So our system collects real-time data, GNSS data from 40 stations across the Korea, and drive the TC and the ROTI, rate of TC index, every 50 minutes. And next year, we plan to launch a web page providing this ionosphere information. Initially, for the first 3 years, we solely rely on GPS data to drive TC, but we are now incorporating TC from QGIS satellite to expand our data coverage equatorward. The QGIS is a regional satellite navigation system based in Japan and consisting of satellites in geostationary and geosynchronous orbit with inclinations. One of our primary benefits of integrating QGIS data is ability to continuously estimate TC at specific points or location, because we can get the consistent signal path from QGIS. This allows us to separate ionospheric variations temporally and spatially. Additionally, we can gather more TC information in southward region, particularly over ocean areas. We also reproduce the TC map from TC observations and also develop TC prediction models using a deep learning approach. And now in this project, we are also building a GNSS scintillation network, a global network of the GNSS scintillation. And the scintillation means a rapid fluctuation of a GNSS signal in amplitude and phase. So currently we have 2 stations in Korea and 1 station in near equator, Micronesia, and 2 stations in Antarctica. And we will build our network in Australia, and hopefully we can get more stations for scintillation in Taiwan. So anyone or any institute are interested in our scintillation network, please contact me. Yeah, we will welcome all the collaboration to build up our global network of the scintillations. And we are also conducting experiments about the gathering or collecting GPS or the scintillation data using a shipborne GNSS. With the collaboration with other research institutes, we deployed our GNSS receiver and scintillation receiver to the research vessel. And the research vessel, they regularly they goes to the ocean and collect the data for a couple of months and came back to the Korea. So we got initial results from those the data, these TC variations from GNSS data, and also these scintillation results from the scintillation receiver. So we will keep this experiment to assess the availability of GNSS data over the ocean. Yeah. So through this our monitoring system, we detect ionospheric perturbations by Tonga volcanic eruption a couple of years ago, about 2 years ago. So we published the results in the GRL. We also detect the ionospheric perturbation by rocket launch. So this animation shows that plasma density depletion due to a rocket launch from Korea. And now I will introduce the rocket, a spaceborne Aurora airglow imager. If you go to YouTube and type International Space Station or the ISS and Aurora, you can find many stunning images or the movies of Aurora from the International Space stations. Aurora is very beautiful, and then I'd like to see every time. But this aurora observation is very important for us, especially for the space weather scientists as well. Why? Why is it important to observe the aurora? As you may know that the aurora is kind of the index of sudden changes or disturbance of a geomagnetic environment or the space weather. So the aurora, I believe that many of you are familiar with the aurora and their generation mechanism, but I may explain briefly. The high energy particles from the sun, they are coming into the Earth's atmosphere and they hit the atmosphere. So, and then the atmosphere, they emit the light, and that's the aurora. So that means if there are many, there are high energy particles that come into the atmosphere. That means there are many energy input to the atmosphere. The aurora can expand to the equator world, and their intensity are very bright. So we can this aurora observation will be the essential for the space weather, the prediction. So especially to identify the aurora over, which is the auroral zone, the location of the aurora occurred. To identify the aurora oval or the boundary of the aurora oval is kind of essential parameter to predict the space weather. So that's why we are building up the aurora imager from the space. So this is overview of our rockets. Currently, we are building up for the satellite. The rocket is a wide field aurora imager, and the field of view is 90 degree. Actually, this is kind of a huge because before then, most imager or the camera for the aurora or airglow, their field of view is only limited to 23 or 25 or something, but ours are 90 degrees. So that means if we go up to the 600 kilometer, the altitude of the satellite, and then the field, if the camera has a field of view of a 90 field of view, and you can expect the observation SWAT, the image of the SWAT will be more than the 700 kilometers. So this camera to provide observations in two the main spectral wavelengths. One is this camera observed the green line, green aurora, and the red aurora. And then the other one is they just camera without any filter. So the science goal is the understanding the response of the ionospheric and thermospheric system to external and internal forcing. And the technical goal is demonstration of the all-sky camera performance from the space. Because in the ground, there are all-sky camera network to observe the aurora, and their field of view is 180. That's because that's because we call it the all-sky imager. So we demonstrate the same type of the camera from the space. And then I briefly introduced the CAS-3, the satellite for the rockets. So this CAS is a spacecraft platform for the small satellite, and the mass is about 500 kilogram. The mission life will be more than a year. And currently we have 3 payloads for the CAS-3. The first one is the rocket, our camera for Aurora and Algol observation. The other one is IMF. They observe the plasma density and the magnetic variations. And the other one, the biocabinet, is the first the payload for space biology in Korea. So these CAS-3 and rockets will go to space next year, the late next year. And then now we are building the flight model for the satellite. For Aurora observations, there are many observations of Aurora in both ground and space. But ground observation provide high resolution images. This is images from the Themis network. But mostly the ground observation is very limited to the weather condition and the location and the coverage of the observation. But the space observation, they can provide a very large scale view of Aurora. So for example, the DMSP SUJI observations, they provide those kind of several or the more than 1,000-kilometer SWAT image of the Aurora. But the problem is usually these type of a spectrograph provides only low resolution, raw spatial resolution, and the local time is very limited because the satellite they have their own orbit, and usually they cover 6 or 10 local time. But the Aurora is very active near noon, so there are some that we need some improvement for the observation. So we are thinking if we deployed optical imager like a ground-based observation, can we obtain high resolution imaging from space? So that's why we started this rockets project. So primary objective of this rockets is identification of Aurora over boundary and Aurora shape in visible wavelengths. And also from green line observation, we can detect atmospheric gravity waves and a plasma bubble and the MSTID as well. This is a brief description of the system. The rockets consist of 3 lens assembly. The 2 of them, each of them, they observe the green line and red line, and the last one, they observe the Aurora for full visible spectrum without a filter. So right side shows that optics design for each lens assembly to observe the green and red line. The F number is 1, and to keep the main rays, because our field of view of our camera is very wide, 90 degrees. So we need to keep the rays parallel to the filter. So we apply the telecentric optic design to do that. And also, this is onboard computer. this is kind of a brain of our payload. So this onboard computer is already tested for the other space mission, like a balloon mission, and then the International Space Station missions with the collaboration with NASA. So those are snapshots of our rockets. So 3 lens assembly, and then there are images or pictures from the environmental tests, like a vibration test and the shock test and the thermal vacuum test. And those right side images are some kind of a test image after assemble of all the lens assembly. So this is operation concept. The rockets primarily turn the nadir to the Earth, observe the Earth during observation in night side, because this is an optical camera. We cannot observe the aurora in day side because the sunlight is too strong. So in day side, the satellite align with the sun to charge the solar panel. And then during the reorientation from sun to nadir pointing, the rockets will also observe the limb of the aurora. And we are planning the coordinate observation of the aurora, especially the COPRI in different institutes in Korea. They operate the all-sky imager in Antarctica, Jangbogo Station. So we will assess the rocket's observation by the coordinate ground observation in Jangbogo Station. And this is the location of the Jangbogo Station. And Jangbogo Station is located in the aurora oval. So almost every day they will observe the aurora. So from those coordinate observation, we will study the evolution of the aurora structure. We also plan to investigate aurora boundary with the collaboration with Johns Hopkins University, APL. So they are operating FUV imager, DMSP SUJI, and timed GUBI. So we will compare the visible and FUV observation to confirm the aurora structure in different wavelengths. And we will do construction of a full aurora boundary based on the partial aurora imaging using a rocket and SUSI as well. Oops. Yeah, this could be the last slide of my presentation. And then lastly, I will show that I will share the information of the new space mission Athena using the rockets and the FUV imager like DMSP and SUJI and GNSF radio occultation receiver. We are planning to build a satellite program, new space program to observe aurora and the Earth atmosphere. So the primary goal or objective of this Athena mission will be to identify the aurora in full visible spectrum, in visible and far ultraviolet and near infrared as well. And the other goal of this Athena will be a detection of atmospheric gravity waves in global. To do this, rockets plus the next version of rockets will deploy the channel. We will add one channel for near infrared observation. So to do that, we expect those kind of images. The color bar, the color one should be a spectrograph FUV image for the aurora, and this the monotone, the observation will be the rockets plus image to provide very fine scale structure of the aurora. So now we just initiate Athena program. So I want the Taiwan, if the Taiwan is also interested in collaborating with this space program, just let us know. Yeah. The Athena will be an international project, international space mission. So we really need international collaboration with many countries. Okay, thank you. I think that's all. My presentation.
All right, thank you, Wookyoung. Very interesting talk. So first of all, I have many questions and follow-up discussions with you probably.
Yeah.
But first I will, yeah, I would like to invite if anyone in the audience would like to ask Dr. Wookyoung Lee question first. Please turn on your mic or unmute yourself, and then just go ahead and ask questions. Or if you're too shy, you can also leave a message in the chat and I will repeat it for you. So I can see my students seems to pass the ball to each other. Someone like to ask questions? They're not too shy?
Well, actually, I think that the students are always shy. They don't ask. But actually, my email address is, I don't know why my presentation doesn't work anymore. Yeah, here. So my contact information is Wookyoung Lee and WKLEE kashi.re.kr. So anytime you can send me a mail about our program and project, and especially we are very welcome for how to say exchange student kind of. So if we some kind of program to exchange our students, that will be a good opportunity to collaborate
Oh,
with each other.
that would be great. I bet my students would be very interested in doing so to
Really?
visit Korea. I think so. I think so. Okay, I guess someone's wanted to ask questions. Ray, you want to go ahead?
Oh, yeah, sure. Can you hear me?
Yep.
Yep.
Yeah. Okay. There's like one question I want to ask. Like, is like these aurora observations, is this mainly focused on like both poles of the Earth, or like only like in the South Pole or North Pole?
This aurora observation.
Yeah.
Okay. Yeah. Basically, that is your first question, right? And do you have another question? You want asking?
I have like another questions.
Oh yeah, sure. Go ahead.
And there is another questions, like you're mentioning like in a previous slide, like you're using deep learning approach to like for an ionosphere monitoring. Yeah.
Oh yeah. So well, actually, I skipped many parts of this our project because the lack of time. Yeah. So currently, well, actually, we already published the two papers. The first topic is yeah, the producing the full TC map from the partial TC observation using a deep learning approach. We use the DC GAN and Poisson blending. And the other one is recently this paper has been published, and then we developed a short-term prediction model for TC using the convolutional LSTM. Yeah. So your question is, sorry for interruption.
Yeah, and the data that you're using is from like your like observation stations.
Oh yeah. Well, actually, the part of that in Korea there are more than 160 stations, GNSS stations in Korea, and then but among them we only use the forest stations. And then because we think that the forest stations observation should be enough to generate or produce the TC map in our data coverage. And the 9 of them, of course, we operate GNSS data. To build up this model, we only used 9 stations of data. Our yeah, right. That's you're asking.
Yeah, that's my question.
Yeah. In the previous slide, I was mentioning about the regional GNSS network operated by CASI, and we have 9 stations for about more than 20 years. We have been operating the 9 stations more than 20 years. So that's why we have a lot of huge data set for the GPS data, and then we calculate the TC from, yeah, it's almost for 20 years of data we have. So based on the data set we developed, we're building a TC prediction model using a deep learning approach. But the stations, yes, only 9.
Okay, thank you.
Yeah.
And I can see that. Did you use IRI for the entire background?
Oh yeah, yeah, right. The background model will be IRI, because as you know that for our technique, deep learning technique, we need full to train the data set. We need a full TC map, but the observation cannot support the full TC map in our coverage. So that's why we use the basing model of this is IRI. Well, we use the IRI for the background model of ours, and then we adjust the IRI trained model to the observation, and combine the observation and the final DC GAN model.
So when you evaluate how accurate the predictions are you evaluate at where you have the observation, or are you evaluating based on the entire 2D map?
Entire 2D map. So actually, this is forecasting one of the results for forecasting performance. This is a ground truth, which is based on the observation. And then this is our the prediction result, forecasting result. And you may see that their pattern and their the variation intensity TC is very almost similar with each other. Yeah. So not only one station, we compare the whole area of the TC map, two-dimensional map.
That's very interesting.
Mm.
Okay. Any more questions for Dr. Wookyoung Lee?
Actually, it's one more question for the previous students ask me is, yeah, well, the rocket, yeah, Pole region. Yeah, rocket is a space-based, the payload, you know, the satellite payload, and then they observe both the north and south. So is this question, is this the right answer for your question? We look both.
Yeah, and if there's like strong solar activities, will you like expand your like observation region?
Oh, your question is if there is a solar storm, like a geomagnetic storm. Well, actually, I cannot catch your question exactly. So can you repeat? Could you please repeat your question again?
Okay. Like if there's like a strong, yeah, like a solar storms. Is this camera is operating all the times?
Oh yeah. Of course, yes. We our camera, we can take a picture of the aurora It's all the time. Not all the time. Only night side. Yeah, only night side.
Oh, I see.
Yeah, but usually it's the most portion of the day. So the duty cycle is almost more than the 60% per day. So yeah, we keep operating. We keep operating camera, so we can observe the aurora in every orbit from north to south.
Okay.
Okay.
Mm. Okay, then my questions.
Yeah, your question.
So I see you've been how long have you been collecting data GNSS data from ships
From ships,
and
it's about.
yeah, and are
Mhm.
you going to incorporate those data into any one of your space weather monitoring in terms of TEC or predictions?
Yeah, actually, we are. You mean the ship, right?
Yeah, ship.
Ship data. We have actually 2 years of experiment data. Uh,
Mm-hmm.
I remember the so because we started those kind of the experiment from 2021 or something.
Mm-hmm.
So we already have 2 years of data, and still we are investigating. We are processing. Where is that? We are processing. Processing the TEC and scintillation index, so for just a research purpose. But
Mm-hmm.
if there is anyone who is interested in our uh, data, the shipborne GNSS data, we can collaborate.
Ooh, really?
Yeah, sure. Well, why not?
So in terms of the frequencies for the GNS receivers, do they receive like 50 hertz or 100 hertz of the data?
Oh, actually, the scintillation receiver, we operate the 50 hertz data, but the receiver, they support 100 hertz. You mean the
Okay.
frequency, right?
Yeah, the yeah, yeah.
Sampling rate. Yeah,
Right.
100. Yeah, receiver support 100 hertz.
Okay, so that's very cool. So definitely we should talk because
Oh,
we will soon start some well, probably very preliminary as well, but we will soon start our receiver here to see if we can get some scintillations. I mean, in our group to see if we can get some first-hand scintillation data to start some research in this area. So that would be because I see the route of the ships. So
yeah,
it's
sure.
coming. It seems it's going all the way south to east of Taiwan.
Oh,
So
yeah. And also we have a go to the Indian Ocean as well.
yeah. So
And
if in
this
the
is,
future, when after we set up, maybe there'll be some overlapping of the observation time. So maybe there'll be something to start with. Maybe.
yeah. That could be a good idea to collaborate with each other about this topic. And you are saying that you already have a receiver scintillation network scintillation stations in Taiwan in your area inside
Uh,
NC.
we we we've got something, and it's capable of doing 100 hertz. But we're still testing it because we just recently got it. So my students, who you might see in the camera, in that lab,
Mhm, mhm.
they will soon, maybe in a few days, they will start putting the receivers on the rooftop, start
Oh,
doing some testing to see if we can run long term, and then see how the data quality is. So we will do some benchmarking before we really would put it to use and have and claim we find something interesting scientifically.
so
But
you made your scintillation receiver by yourself? I mean, in your lab?
kind of some of our the seniors in graduate from our department. So who
Oh,
is helping us doing that? Yeah.
that's very interesting because I can deploy our receiver to your station, and then maybe we
Really?
can compare it directly.
That would be awesome because we also got one. We will be So yeah, related questions. We are going to Texas next week for
Oh,
the solar eclipse.
me as well.
You as well?
Oh, you will test your receiver in Dallas?
We were yeah, sort of. So we will take a few receivers to Texas, and we will deploy one or two maybe. We have three, but two identical. One is different. One is the higher frequency ones. So we'll put one set of receivers at UTA
Mm-hmm.
and the other one at UTB,
Mm-hmm.
and Fabiano will lend me or give me another his SimPi 3.0.
Okay.
So I guess by the time we got back to Taiwan, we'll have a lot of receivers. And if you are going to give me one, that'll be great.
Yeah, actually, in Dallas, I'm thinking now I'm preparing. Now I'm thinking to bring our receiver to Dallas and then
Mm,
to observe the solar eclipse. So I'm considering to do that for, well, because our receiver is the Septentrion. It's a
mm-hmm. Yeah,
polarized five. There's very the good receiver and then the high performance receivers. So that the observation can be maybe reference data
yeah,
for your receiver, right?
yeah, that'd be
Evaluate
great.
to evaluate. Okay, let's keep
So
talking
I
about.
guess, yeah, I guess, yeah, we're seeing, so I'm bringing two students of mine to
Mhm.
Texas. So I guess we will meet there and then
Uh-huh.
we'll have dinner or lunch together.
Oh, okay.
But
So
related to solar eclipse events, are you going to run the, so just in case the wave, if the gravity wave, the scale of the gravity wave is big enough, maybe the structure or the perturbations will actually propagate to Korea. So, any plan of investigating those data from your night stations in the same event?
so actually, it's you are thinking that maybe solar eclipse can generate the gravity waves, right?
Mm-hmm.
That's your hypothesis, right? But
Mm-hmm.
well, actually, there are not many observation evidence for those that. So
Not
I
gravity waves?
oh many gravity waves during the solar eclipse.
Yeah,
Okay, so how I don't know they can whether they can affect the ionosphere or not. The intensity of
I
the
believe so.
perturbation. Yes, I know that
Yeah.
some research showed the gravity wave signature in the TC map, but we are not sure that is true or not.
So are you going to come back maybe like half day after the eclipse to see if you can see the structure inside the Korean sector as well, the fluctuation. But I guess it would be very hard to distinguish from the background MSTID.
Yeah, yeah, sure, sure. Yeah.
Okay.
Oh, okay.
Probably discussion for next time.
Yeah.
All right. Other than my questions, anyone in the audience wants to last chance for anyone in the audience to ask questions?
Okay, maybe it's
No.
time to go
If
home.
not, no, not yet. But it's 5 o'clock for Dr. Lee. So
That's okay. I'm going to work tonight.
wow. Okay, so if no more questions, once again, Wookyoung, thank you so very much for accepting our invitation to give this talk, to have really helping us to learn projects at Cassie better,
Sure.
and really, as you say, hopefully we can kick off some interesting scientific collaborations in the short future.
Yeah, I really hope so. I really hope so, especially for the scintillation network. Yeah. And also,
Yeah,
we are
and
welcome for the joining us for the Athena mission. Cici, I know that you are kind of the gravity wave, the person, and the one of the main observation for Athena is the gravity waves.
mhm,
So I think that you should
I
join.
should,
You
yeah,
and your group should join to our project.
yeah, they probably can't wait to go to Korea to for the exchange
Post,
student thing.
Postbar,
I,
postbar. How many
Close
students
by.
will be coming to Korea.
No, only me this time. But we'll see what funding opportunity I can get, and maybe we can talk to see how to send exchange students over.
Yeah, sure. Okay.
Mm-hmm.
Thank you for inviting me to this seminar. And I'm so
Thank you for
sorry
accepting the
for
invitation.
the delay of a presentation.
Well, you managed the time well. You managed time well.
Yeah.
All right. Thank you, Wookyoung. I'll see you in Korea soon.
Okay. Thank you. See you.
Okay. Thank you,
Professor Lee.
everyone,
Thank
for
you.
joining.
Thank
Yeah.
you.
Thank you. Bye.
Thank you. Bye bye.